Hello everybody, welcome in this new video. Today we're gonna discuss together heat engines and we're gonna see a brief review of thermodynamics. So let's begin together. First, let's know what's thermodynamics. It is the science of thermodynamics, deals with the relationship between heat and work. It's governed by two laws, neither of which have ever been proved. On the other hand, no violations of either law have even been observed. We're gonna begin with the first law of thermodynamics. The energy can be extracted from a process can never be more than the energy put into the process. This is what the first law of thermodynamics said. In other words, the energy out is equal to the energy in. This is essentially the law of conversion of energy. I explain more. Energy can be neither created nor destroyed. It can only be converted from one form to another. Next, let's discover the second law of thermodynamics. The second law of thermodynamics said that the first law is concerned with the totality of energy in a process. The second law tells us how much work we can extract from a given amount of heat. Carnot's statement was to the effect that we cannot convert all the available heat into work. The second law is also concerned with whether a process can occur at all. For example, heat will always flow from a high low to a low temperature. A gas under pressure will expand. Compression does not occur naturally. Let's now discover the heat engines. A heat engine is a device for extracting work from a hot fluid. For example, a car engine extracts power from the combustion of fuel with air. A steam turbine extracts power from steam. Both of these function by allowing a hot fluid to expand so as to cause motion in a critical component of the engine. In the process, a high-grade energy is said to be degraded to lower-grade energy. Passing now to discover an ideal heat engine. Seeing together this picture, the diagram on the right represents an ideal heat engine. Heat is added at constant temperature to the fluid at the high temperature source. The fluid flows throughout an expansion device where work is done, and the temperature of the fluid falls from the high temperature to the low temperature. Heat is then rejected at constant temperature at the low temperature source. Now let's see a closed cycle of a heat engine. The cycle in the previous slide is known as an open cycle. The closed cycle here has 4 stages. Is a thermal heat additional? adiabatic expansion, isothermal heat removal, and adiabatic compression. Just to know, isothermal means a constant temperature, adiabatic means perfectly insulated. Now let's discover the Carnot engine. The cycles above are examples of the Carnot engine. In the Carnot cycle, all processes are reversible. In a Carnot engine, the maximum work that can be done, and hence the efficiency of the ideal engine depends on the temperature, the height one and the low one. The efficiency of a Carnot engine is given by this formula. The temperature is in the Kelvin or absolute scale, and this efficiency is called the Carnot efficiency. Passing to know the practical heat engine. The Carnot engine represents the theoretical limits and is not a practical engine. The main limitation of the Carnot engine are the processes in all four stages are reversible. For this to be the case, they must all take place infinitely slowly. The work extracted on expansion is equal to the work required for compression, so no net work is extracted. A practical heat engine has a lower efficiency than a Carnot engine, but can make more effective use of the energy in the hot fluid. Passing to the second part of practical heat engines. Practical heat engines include the Rankine cycle, basis of steam engines in power stations, Otto and diesel cycles, internal combustion engines, and gas turbine. These have lower efficiencies than the Carnot cycle, but are permit useful work to be extracted. Discovering now the Rankine cycle. This has two differences to the Carnot cycle. There must be reasonable temperature differences in the boiler and condenser to ensure that heat addition and rejection occurs at an acceptable rate. The turbine executes is completely condensed and returned to the boiler by a pump. This uses very much less energy than a compressor. These results in lower efficiencies than the Carnot cycle, but permit useful work to be done. Seeing now other cycles. Otto, diesel and gas turbines are involved in initial compression stage, but are otherwise open cycle processes. Combined cycle gas turbine. We have this combines a gas turbine with a Rankine cycle to maximize the work extracted from the fuel. Efficiencies are much closer to Carnot efficiencies than in other practical cycles used to date. And finally, we can conclude that work is heat and heat is work, and all the heat in the universe is gonna cool down. Yeah, that is entropy, man. Thank you for watching this video. I hope that you like it. Don't forget to put like and to subscribe to my channel to receive all the videos. Thank you so much everybody and goodbye.